Welcome to a Code Report HackerRank solution video. In this video, we're going to be going over the solution to problem 4 from week of code 36 entitled A Race Against Time. The problem states, Mason and Madison are in a relay. Mason starts with a baton and Madison receives the baton at the final destination. There are students in between Mason and Madison and each of their heights is given. Mason's height is given as well. The rules of the relay are as follows. The current baton carrier has an option to hand over the baton to the student at the current position or to continue to the next position. However, if the student at the given position is taller than the current baton carrier, it is mandatory to hand over the baton. It takes 1 second to move between consecutive positions, whether the baton is handed over or not. And if the baton is handed over, there is an additional time and price associated with it. The additional time taken is the absolute difference between the heights of the baton carrier and the student to whom the baton is handed, and the price is given for each student. And the question asks that the baton must be sent to Madison in the minimal possible sum of time and price. Return this sum. And note that for our inputs, the number of students is going to be between 1 and 10 to the power of 5. The heights of these students will be between 0 and 10 to the power of 9. And the prices are going to be between negative 10 to the 9 and 10 to the 9. So prices can be negative. So let's take a look at an example. So in this example, Mason's height, the individual who starts with the baton, will have a height of 5. There's 5 students in total. That's Mason plus the 4 other students. Madison doesn't really count. She's just at the end waiting for the baton. And the heights of the 4 other students other than Mason are given here, 2, 3, 6, and 2. So these 4 students are sort of a visual representation of their heights. And their prices are given below. So we can add their prices to a graph and it'll look as follows. So the orange bars represent the prices and the green bars represent the heights. So we know a couple of things to note is that we know that, at minimum there's going to be a time cost of 5 seconds to get the baton from Mason to Madison, just because it takes 1 second to move from one student to the next, whether you're handing it over or not. So that's, 4 seconds here plus 1 to get it to Madison. Another thing we'll note is that at minimum we are going to hand the baton over once from Mason to the third other student. And that's because this student's height is 6, and according to the rules of the relay, whenever you pass a student whose height is greater than yours, you have to hand it over. So at this point, if we're not going to hand the baton to either the first or second other student, the additional cost here would be 1 for the time, because the absolute difference of their heights is 1, and an additional 3 in terms of price. So it would be a net additional 4 in terms of cost, the time plus the price. And so the way that our algorithm is going to work is that we're going to process the students in reverse order. And basically, using dynamic programming, we are going to store the basically the minimum sum, the answer to the problem, if Mason was actually each of these students. So at this point, if Mason was this student, the minimum time would be 1, because all you have to do is move 1 spot and then you can hand the baton to Madison. And from here, the minimum time would be basically 2, because you have 2 options. You can either just move past the last student and then it's 2 seconds to get to Madison, or you could hand the baton after 1 second passed and then let the final student take it. But this would cost you an additional absolute value of 6 minus 2, which is 4, plus the price of 2, which is going to be 6. So your options are either basically a cost of 8 if you hand it over, or 2 if you bypass this student. So that's sort of the general way that our algorithm is going to work, and we're going to have 2 ways that we process students. Each time we have a student, we're going to push it onto a stack, and any time that we have a student which is to the left of our student that we just processed, we are going to process the students that are less than this student right away in a while loop. And if you're in a case where the student to the left of the student that you just processed is less than, we're just going to continue to push these on the stack, and there's going to be sort of a recursive nature to this function or to this algorithm. So let's take a look at sort of how this whole algorithm would work out if we worked through it on paper. So you can see here that I have these two additional vectors, dp inter and dp final. So dp final is the actual values of what I mentioned before, of if Mason was each of these other students, what would be the answer to the problem at that point. So note that I said, it would be 1 for the last student, 2 for the second last student, and then these are the other values that you would get from the first and second other students. And our answer is going to be in the first index of our DP array, which corresponds to basically the value, the minimum value that Mason can get to Madison in. And this intermediate value is for when we are in the first case of the student where the student has a height that is greater than the previous student that was processed. We're going to have some additional calculations there, which is basically looking at what if we were to pass it down to the student and then have that student go forward in the algorithm. But this could get overwritten if it's just cheaper to walk past either the one student, or if you have multiple students here, like a subset of those students. And sort of this, when you end up with this case where Mason has multiple students that are to the right of him that have a height less than him, or it doesn't need to be Mason, it could be some other student that you've passed the baton after, you're going to, in this while loop, process multiple of these, and it won't just be this one student in this case, so you could have a multiple of these, I guess, students that are processed. So let's take a look at our code example. So there's a lot of code here, so I'm going to try and make this easier to see. So just note that at the top here, we're using a type alias LL to represent the variable long, and we've initialized these arrays in the maximum length of our input, so we don't need to worry about dimensioning vectors and whatnot. So we can get rid of this, and also too, the first 3 lines of code is just initializing the number of students, including Mason, and then reading these values into the arrays that we declared outside of our main function. So I'm going to delete these lines so that we can sort of zoom in on the actual algorithm code, and then also delete the return in the main part of the function. So here we can see that at the top of our algorithm, we're declaring our stack onto which we are going to push the indices of our students, and we're going to process these in reverse order, and it's a pair of 2 long values. So the second long value is basically going to be this temporary value that is going to be used to back out the additional cost in the case where we have a student that has a height greater than the students that were just pushed onto our stack. And so this temporary value gets added at the end here, temp, and it's going to work together with another line. So when we're in the case where we have a student that it's his height or her height is greater than the students we just processed, this line here is going to work with this line here. So if you basically add DPI, which is just the value it would take to get to the end from the current position, plus I minus heights I plus prices I. So you can think of this I and this I as J, and then when we're in the next iteration of the loop, we'll have a different index. The plus I minus I here backs out the 1 second per position. The next temp is basically equal to this, so you can substitute this next temp for this guy. So the DP is just the value it would take to get from that person from the next index, and then the plus heights minus heights plus prices is just the plus heights minus heights is the absolute difference plus the additional cost. So these 2 lines work together in order to get you that additional cost when your student is that you're currently processed has a height that is taller than the student that was just processed. In the case where you have a student that has a height that is less than the student that you just processed, you're going to come to this case. And so this line works by itself. It doesn't sort of have two lines that have values that are offsetting each other. You can see that this j minus I is equivalent to the minus I plus I here. The dpj is just equal to the dpi here, and then you have your plus heights minus heights plus prices. So once again, the absolute difference of your heights plus the price of that student. So note that we're not using absolute value here, and that's because these two basically conditions on how we process the students are based on whether it's comparing the heights of the student that you're currently processing versus the student that you just processed. We know which one's going to be greater, so we don't need to use the absolute function from the math library. We can just subtract them in the correct order. And so basically that's the gist of our algorithm. So you can see the DP, it's just storing the minimum sum if Mason was actually the student I. We're in this loop, once again, we're processing students if the height of the student in the stack is less than or equal to the current student height. And the only other thing to note is in the case where, Mason, we get to Mason, he's being processed now, and the two students to the right of him have heights that are less than his. We have this extra assignment to our temp here, where basically we are always going to set temp to the minimum of temp and next temp, and that's going to take care of the case in our algorithm where we actually, when we're starting with Mason with a height of 2, with a height of 5, we don't want to step down to the first student at a cost of basically an additional 3 in time and 2 in cost. That's going to add to our total sum, and it won't result in the minimum. But for the second student, stepping down to 3 will cost us an additional 2 seconds, and it will give us a -5 in terms of price. We definitely want to do this. And so this line here is basically, it gives us the ability to skip some of the students that are to the right of us when they have heights less than ours, but include others. So that's sort of how you take care of that problem. And whenever you don't have any students in your stack, this line of code basically will give you just the number of seconds it will take to go directly to Madison, or it's 1 second per student. And that is our algorithm. So this, at the end, you will have your answer in the first element of your DP array. And because we're only ever pushing each student onto our stack once, this is going to be a linear complexity. And the only other thing I want to comment on is this is actually this algorithm is a modified version of an algorithm called the NGE algorithm, otherwise known as the next greater element algorithm. So if you want to know more about that, I'll leave a link down in the description below, linking to a Geeks for Geeks explanation of that problem.
As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.